Hello, Math 2 students. In our last video, we figured out that there were 3 ways to test a radical expression to see whether or not it is in its simplest form. The first way is to look at the radicand. If it can be divided by a perfect square, then that radical expression is not in its simplest form. Again, the second way is if you look at the radicand and the radicand is a fraction, then that radical expression is not in its simplest form. And finally, if you look at the expression and there is a radical in the denominator, you know that that radical expression is not in its simplest form. We also learned that there are 4 steps to taking a radical expression that is not in its simplest form and changing it so that it is in its simplest form. And those 4 steps were to reduce, then to separate, then to simplify, and then to rationalize. And the examples that we did only used the first 3 steps: reducing, separating, and simplifying. So today's video will have 3 examples of how to rationalize. You should get out your same notes, and in the rationalize column, be ready to write something down this time. You might need to use the back of your paper, but I would try to keep all of this information on the same piece of paper. Our first example problem is the square root of 3 over 39. And I know that this radical expression is not in its simplest form because the radicand is a fraction. So I'm going to start out with step number 1. I'm going to reduce that fraction. So I have 3 over 39 as my radicand, and I divide the numerator by 3, and I divide the denominator by 3. And the resulting fraction after it is reduced will be 1 over 13. So that's the reduce step. I'm done. But I need to remember, I was only working with my radicand at that point. I still have the square root of 1 over 13. Now I'm going to separate. So I'm going to take my square root of 1 over 13, and I'm going to use the division property of radicals to separate it into 2 different radicands. So when I separate it, I will have the square root of 1 in my numerator and the square root of 13 in my denominator. So the next step is to simplify. Well, there's one great thing about the square root of 1. 1 is actually a perfect square number. So the square root of 1 is 1, but the square root of 13 cannot be divided by any perfect square number. So that's the expression that I have at this point in the problem. Previously, we would have said we're done. So if we look, we have a radicand of 13, no perfect square goes into it. Our radicand is not a fraction, so we're okay on number 2. But on number 3, the denominator of our expression contains a radical. So we have to get rid of that radical in our expression, at least the radical in the denominator. So to do that, we need to rationalize the denominator. What you should remember about perfect square numbers: if you multiply a number by itself, the result, the product of that multiplication problem will be a perfect square number. For example, 5 times 5 is 25. 25 is a perfect square number. So we can do the same thing with radicands. If we multiply a radicand by itself, we will get a perfect square radicand. So when we rationalize, we're trying to eliminate the radical from the denominator, and we're going to do that by multiplying the radicand by itself. So the problem now will look like this. But as you learned about fractions long ago, if you are going to multiply the bottom of the fraction by a number, you need to multiply the top of the fraction by that same number. So when you rationalize, we're going to multiply the top and the bottom, the numerator and the denominator, by the square root of 13. In the numerator, 1 times the square root of 13 is the square root of 13. And in the denominator, the square root of 13 times the square root of 13 equals the square root of 169. And like I said, if we multiply a radicand by itself, we will get a perfect square radicand. And 169 is a perfect square. So now I'm going to simplify that part of the problem. In the numerator, I still have the square root of 13, but in the denominator, the actual value of the square root of 169 is 13. So when we look at our list at the beginning of the problem, our radicand is 13 and no perfect square goes into it. Our radicand is not a fraction, it's just 13. And the denominator does not have a radical sign in it. So this is the simplified version of our original expression. In our next example, we have the square root of 5 over the square root of 54. In this case, we have several problems. That denominator that has a radicand of 54, it can be divided by a perfect square. Also, the denominator contains a radical. So we're going to have to go through our 4 steps of reducing, separating, simplifying, and rationalizing, and use as many of those steps as we need to eliminate number 1 and number 3 so that we can say that our radical expression is in its simplest form. All right, so the first thing I want to try to do is reduce. So I want to find the greatest common factor of 5 and 54. But the only number that goes into 5 and 54 evenly is the number 1. So we can't reduce at this point. Next step, separate. Our problem, it is already separated. We don't have one radical sign with a fraction underneath. We have a radical sign in the numerator and a radical sign in the denominator. So we can skip reducing and we can skip separating. Now we're moving on to the simplify step. So we have the square root of 5 over the square root of 54. And we have to think through all of our perfect square numbers, starting at the end with 225 and working our way down through every number until we find the largest perfect square that goes into 54. And when we go through that process, the largest perfect square that goes into 54 is 9. So I'll rewrite my problem like this. And instead of writing 54, I'm going to write 9 times 6. And then I'm going to use the multiplication property of radicals and rewrite the problem like this. The square root of 5 over the square root of 9 times the square root of 6. And remember, I'm simplifying, so the square root of 9, that is not really a value of 9. The square root of 9 is a perfect square. You can express the value of the square root of 9 without using the radical sign because the square root of 9 is exactly 3. So I'm going to rewrite the problem like this. The square root of 5 over 3 root 6. And now everything is simplified. Number 1, we've taken care of it. The 5 on the top, there's no perfect square that goes into 5. And then the 6, the radicand on the bottom, there's no perfect square that goes into 6. So we're ready to finish the problem, but we're going to need to rationalize to fix number 3. We need to get the 6, that radical, out of the bottom of our fraction. So we're going to start with root 5 over 3 root 6. And the great thing that we discovered in the last problem is if you multiply a radicand by itself, you will get a perfect square radicand. So we're going to multiply the radicand root 6 by itself, root 6. But we know from every fraction problem that if we multiply the bottom by root 6, we have to multiply the top by root 6. And so I will rewrite the problem. Radicand 5 times radicand 6 is radicand 30. And 3 times radicand 6 is 3 root 36. So make sure you pay attention to what happened to that 3, which is a number, and what happened to those radicands, which are 6's. Now we're ready to finish the problem because the square root of 6 is a perfect square. So we will have root 30 in our numerator, and on the bottom we will have 3 times, and we can express the value of root 36 without using a radical because the value of a root 36 is exactly 6. So one step left to finish our problem. 3 is a number, 6 is a number. We can multiply those numbers and get 18, and we'll have root 30 over 18. So now we go back to our list at the top of the page. Our only radicand left is 30, and there is no perfect square that can go into 30. Our radicand is 30, and that's not a fraction, so we're good with number 2, and there's no radical sign in our denominator. So this is the simplified version of our original expression. For our last example problem, we have the square root of 6d squared over 10, and when I look at this problem, I see that the radicand is a fraction. So rule number 2 is the one that is causing us to have to simplify the expression. So I'm going to start out though, and I think I can see on this problem that I'm going to be able to reduce. So if I look at the 6 and I look at the 10, and I try to find the greatest common factor, the biggest number that goes into 6 and 10 evenly, that number is going to be 2. So I'm going to divide the 6 by 2, and I'm going to divide the 10 by 2, and now rewrite the problem like this, 3d squared over 5. Okay, now I still have a fraction underneath the same radical sign, so in the next step I'm going to separate it and rewrite the problem like this, the square root of 3d squared over the square root of 5. So I've separated it. Now I'm going to try to simplify it. So when I look at the square root of 3d squared and I look at the square root of 5, there is no perfect square number that goes into 3. There's also no perfect square number that goes into 5. But d squared, that is a perfect square, because remember, when you're working with variables, the perfect square of a variable is that variable squared. So I'm going to rewrite my problem, and this will be the simplified version. I'm going to have d on the outside, root 3 over root 5. So now the next step is just to rationalize to get that radical sign out of the denominator. So I'm going to start with d root 3 over root 5. And if you multiply a radicand times a radicand, you'll get a perfect square radicand, and then you can express that value without using a radical sign. So I'm going to multiply the bottom by root 5, and I'm going to multiply the top by root 5. If you haven't noticed yet, that just means we're multiplying by 1, because we're multiplying by a number that has the same thing on the top and the bottom. So we're not really changing the value, we're just arranging the problem so that's in an acceptable form, the simplest form. So on the top, our numerator, we're going to have d root 15, and in our denominator, we're going to have root 25, which is a perfect square. So we can express the value of the square root of 25 without using a radical sign. It will just be d root 15 over 5. So now if we go back to the top of the page and we look, our radicand is 15. There are no perfect squares that go into 15. Our radicand is 15. That's not a fraction, so we don't have to worry about that. And in number 3, there is no longer a radical sign in the denominator, so this is the simplified form of our original expression.